In this video, we're going to discuss calorimetry. So calorimetry is the study of heat transferred either from a chemical or physical process or heat transferred into a chemical or physical process. And why do we want to study calorimetry? Why do we want to study heat transfer? Well, there's a number of applications. Some of those include the development of more efficient and effective fuels. Another would be measuring the energy content in food. So if we want to know how many calories a certain food substance has, we use calorimetry experiments to measure that. Another important biological application is that calorimetry can be used to measure the interactions between drugs and proteins. If a drug interacts with a specific protein, a small amount of heat is released, and calorimetry can be used to measure that and then determine whether the drug is binding very efficiently or not very efficiently to that particular protein. So there's a lot of medical and biological applications for calorimetry. So calorimetry takes advantage of the first law of thermodynamics, also called the law of conservation of energy. And this law tells us that energy can neither be created nor destroyed. It can only be converted from one form to another. It also means that energy can be transferred from one thing to another, but the amount of heat or energy gained must be equal to the amount of energy lost. We cannot create or destroy new energy, but we can transfer it. Stated another way, it tells us that the total internal energy of an isolated system must be constant. So before we move on too far, let's define a couple of very important thermodynamic terms, such as the system. In thermodynamics, a system is defined as the substance or substances that are undergoing the chemical or physical change. In other words, it's the thing that you are studying. If you're studying a chemical reaction or a drug-protein binding, the system is that particular thing that you're studying. Now, we also have to talk about generally what we call the surroundings. The surroundings is defined as the other components of the measurement apparatus that serve to either provide heat to the system or absorb heat from the system. It's pretty much everything outside of our system. So remember, with calorimetry, we're talking about heat transfer. So heat can be transferred out of the system to the surroundings, or heat can be transferred from the surroundings into the system. However, the amount of heat transferred is always constant or equal to the amount of heat gained. Now, the sum of the system and the surroundings, so everything in thermodynamics, is what we call the universe. So we already stated that energy can neither be created nor destroyed. Therefore, the overall energy change for a chemical reaction must be zero. So think about that. Mathematically, we could state it like this. The Q, the heat lost or gained by the system, plus the Q lost or gained by the surroundings is equal to zero. Restated, if we restate or rearrange this equation, the amount of heat that is lost by a reaction, so let's say a chemical reaction loses heat, we call that exothermic. The heat lost by a reaction must equal the amount of heat gained by the surroundings. So if we rearrange this a little bit, we get negative Q of the system is equal to positive Q of the surroundings. The negative sign means that the heat is being lost by the system, and that's equal to the heat gained by the surroundings. Or if we state it another way, the heat gained by the system would be equal to the heat lost by the surroundings. In other words, the heat must be constant. But here again, we're talking about a transfer of heat. So studies involving the release or absorption of heat are often performed in an apparatus called a calorimeter. So if we're going to actually study heat transfer, we generally need to use something called a calorimeter. Calorimeters are very well insulated. We want to study heat transfer, so we don't want interference from coming in from other sources of heat. So calorimeters must be very well insulated devices which allow accurate measurement of changes in temperature caused by the reaction process being studied. So if something is gaining or losing heat, if our system is gaining or losing heat, there should be a change in temperature. We want to be able to relate that change of temperature to amount of heat gained or lost. So temperature changes. So the calorimeter measures essentially how much change in temperature there is in a chemical or physical process. The temperature changes can then be used to calculate the heat transferred using the formula for specific heat capacity or heat capacity, either one of these, which we've talked about previously. So Q, the heat absorbed or released, is equal to the specific heat times the mass times the change in temp, or Q, the heat absorbed or released, is equal to the heat capacity times the change in temp. Now, when we talk about calorimetry and calorimeters, there are two major types. There are calorimeters that operate at constant pressure, and there are calorimeters that operate at constant volume. The constant volume calorimeters are often called bomb calorimeters. Now, we'll see why these are important as we continue on in our discussion of calorimetry and thermodynamics, but let's introduce those concepts here. So first, there's what we call the constant pressure calorimeter. The reaction that's being studied, the system, the reaction is carried out under constant pressure conditions. So here we would have a representation of a constant pressure calorimeter. In this reaction, if gases are generated, the gases can expand or contract. So in other words, this lid is generally very loose, so the gases can expand or contract. In other words, the gases can expand and push outward, and therefore they can do work on the system. Now again, we'll talk about this more as we go along, but it's important to appreciate that constant pressure calorimeters allow the gases to expand or contract, and therefore they can push out or in, and work can be done. The other type of calorimeter is the constant volume. So the volume is constant. The volume cannot change, also called the bomb calorimeter. So the reaction is carried out under conditions of constant volume. So in a bomb calorimeter, it's sealed up very tightly, and the reaction is performed in a reaction vessel where any gases generated cannot expand or contract, therefore they cannot push out and do work on the system. So no expansion or contraction can occur. But again, when these reactions occur, heat can be released or absorbed. So let's say heat is released from our system into the surroundings, in this case water. The temperature of the water would rise, and we could use our specific heat equations to calculate the amount of heat that was released. Same thing with a constant pressure calorimeter. We translate the changes in temperature into changes in heat. Now we'll look at those calculations a little later. In this video, we just want to again introduce you to the concept of calorimetry and the different types of calorimeters. So we'll talk about the others later, but be sure you appreciate what calorimetry is, some of its applications, and the different types of calorimeters.